9.3. So today, guys, we're going to talk about how two planes can intersect or not intersect, right? So in the first case, I've got two planes, pi 1 and pi 2, and you can see that they are parallel, right? So they are, they're not intersecting at all. So hence there would be no solution there. What would be the same in terms of those two planes? What would they have in common?
Normal.
Sorry, nice and loud. Wait, did you say normals? Yes, the normals would be the same as with direction vectors, right? So the normals would be, they would have the same normals, okay? And why am I talking normals? Because we're going to be dealing with Cartesian equations, okay? All right, then I have two planes that are coincident. So that means how many solutions will exist? Infinite number. Okay, infinite number of solutions. And when you're talking about a Cartesian equation, if this is the case, then that means they're going to have the exact same Cartesian equation. Now, one could be a multiple of the other, but when it's reduced, it will be the exact same Cartesian equation. Okay, so same normal, and the d value will be the same as well in the Cartesian equation. And then you have two planes that intersect. And I want you guys to notice, when they intersect, how do they intersect? Do they intersect at a point? How do they intersect?
Out of line.
Yeah, they intersect in a line. And we know that planes go on forever and ever and ever. Like we show a little section of it, but these planes would extend forever and ever and ever. And so when two planes intersect in a line, we know lines also extend, right, in both directions. And so therefore we have an infinite number of solutions along a line L, okay? Now, when you're looking at the Cartesian equations, of course, here we would have normals that are not the same. Okay, the normals would not be the same, obviously, because the two planes are not parallel or coincident, right? Good. Any questions about this? Okay, good. So let's take a look. So here, guys, two parallel planes, no solution, same normal. Two coincident planes, infinite number of solutions, same normal and same d value from the Cartesian equations, of course. And two intersecting planes, infinite number of solutions along a line L. Okay? The normals are different. All right, so determine the solution set to the intersection of these two planes. What am I going to do? So these are my three situations. I got to figure out which one this is. So what should I do first? Well, I'm given Cartesian equations, so I'm going to look at the normals. And when I look at the normals, I want to see if one is a scalar multiple of the other, or if they're the same, because that's going to help me narrow down my selections, right? So when I look at the normal of the first one, I see that it's 1, negative 1, 5. And when I look at the normal of the second one, it's 3, negative 3, 15. But that can be reduced, can't it? So that second normal now, I can divide them all by 3, and I notice I get 1, negative 1, 5. And so really the normals are the same. So that leaves me now with two of the three choices. It's either going to be the first or the second choice, and I have to determine which one. Okay, so since we see that one is a scalar multiple of the other one, the planes are either parallel or coincident. So how am I going to figure out whether they're parallel or coincident? What do you think? There's a little hint here. What do you guys think?
Check the d value.
Yeah, check the d value, right? Because if the d value is the same, it's the exact same equation. But if the d value is not, right, when that second equation is reduced, then we see that they are not coincident. So let's check. So I've got d1 that's equal to 7. I've got d2 that's equal to negative 21. But we know that that's 3 times, right, the other equation. So let's take a look. And sure enough, 7 times 3 is negative 21. And so we can see that the planes are coincident. They're exactly the same. Those two equations basically are exactly the same when the second one is reduced. And so therefore we have an infinite number of solutions. So now how do we write this? How do we write the solution set? We're going to write it in parametric equations. Okay? And what you're going to do is you're going to choose parameters for y and z. So using parametric equations, from here, what would x equal? So here, I'll write them here. I have x minus y plus 5z equals 7. So what I can now do is if I'm choosing parameters for y and z, I'm choosing y to be s and z to be t, then I can say that x minus s plus 5t equals 7. And that means that x equals s minus 5t plus 7. Okay, so again, guys, we're choosing parameters for y and z. Y equals s and z equals t. So for those of you that looked at that second method in chapter 8, you remember there was an example where I showed it two ways. This is what we did for the second way. We chose the two parameters for y and z. So that's what we're doing here. And so my solution set is x equals s minus 5t plus 7, comma y equals s, comma z equals t. St is an element of real numbers. Okay, infinite number of solutions. Okay, are there any questions? Okay. Example 2. Determine intersection or the intersection of these two planes. So I have two planes here. What should I do? Two planes given.
Normal.
Yeah, check the normals. So my normal from my first one, 1, 4, -3. Normal from the second one, 2, 8, -6. So reduce the second one as we see that we can. And you see that you have the same normal, right? It's multiplied by 2. This whole equation is multiplied by 2. And so now we're going to do the exact same thing we did in the last example. We're going to check if that d value, -11, is also multiplied by 2. And it's not. And so because it is not, we see that it is, we see that therefore it is parallel and not coincident. And since they are parallel, then we know that we have no solution. Okay. Are there any questions? Okay, good. Simple enough, right? Okay, example 3. Determine the intersection of these two planes. Again, Cartesian equations, two planes. So now I have to take a look at the normals, just like we did in the last two cases. So I look at the normals. I've got 1, 2, 7, 1, 3, -3. No chance that these are parallel or coincident, right? We don't have the same normals. And so therefore, we know that they have to intersect at a line. So now, if they're intersecting in a line, how many parameters do I have? Think back to a vector equation of a line. How many parameters do you have?
1.
Yeah, you only have 1. And so now we're in our solution. We're only going to have 1 parameter and not 2, right? When we had the solution for an for a plane, we had the 2 parameters. Now we only have 1 because the solution is a line. Okay, so how can I solve this? Well, I can do this 2 ways, right? I showed you guys how to solve systems of equations with matrices. So you could use a matrix to do this, or you could use substitution or elimination. I'm going to show both. Okay, so method 1, elimination. So here are my 2 equations. I notice that my coefficient of x is the same, and so I can go right ahead and just subtract my 2 equations, which gives me -y, right, 2y minus 3y, plus 10z, 7z minus -3z, is equal to 4 minus 1, which is 3. And there's my equation. Y is equal to -3 plus 10z. Okay, now we want x in terms of z, right? I have my solution for y. Now I need x in terms of z. So I sub my equation 3. Let's go here. Sorry, excuse me. My equation 3 into number 2, and I solve. solving from here, notice I subbed in for my y. Solving from here, I now have x equals 10 minus 27z. So I have y equals negative 3 plus 10z, and x equals 10 minus 27z. So what's my parameter here? What am I going to use? What am I going to say? What do you guys think? Look at the way it's set up.
Let c equals to t.
Yeah. So I'm basically deciding from here, I see that y equals negative 3 plus 10z. So that means I'm going to let z equal t. That's what's happening here. And so now I say, well, let me get x in terms of z, because that's what I'm going to use as my parameter. And so there's my solution set. So from the parametrics, I have x equals 10 minus 27z, but I'm going to let z equal t. And so I have x equals 10 minus 27t. And then I already have my y equals negative 3 plus 10z, and I just sub in the t. Okay, so here it is with commas, z equals t. T is an element of real numbers. So that's what it's going to look like when you're solving using substitution or elimination. I didn't have to use z to be t, and you're going to notice I have a note here for one of the questions in the homework where they choose y. For consistency, well, I mean, you guys aren't writing a test, but in your homework, usually what I say is for consistency, always let z equal t. Right? Just so that everyone's doing it the same way. We don't really have a test that I'm going to have to be marking other than multiple choice right at this point, so it doesn't really matter. Okay, method 2. So what would this look like if I was using a matrix? So I go ahead and I put my two equations into the matrix. And so we learned yesterday that the first thing I want to do is get that one in the top left-hand corner, right? Row 1, column 1. I have it. So now I go down the column, I have to make that second one a 0. So how am I going to do that? Well, I'm going to take row 2 and I'm going to subtract row 1. Quite easy to see, right? And so I'm going to be left with 0, 1, negative 10, negative 3 in the second matrix. Then from here, I go to my next row and I need a 1, column 2, row 2, and I have it. So now I just have to make that 2 a 0. So how am I going to do that? Well, I'm going to take row 1 and I'm going to subtract 2 times row 2. And notice what you get here. You get 1, 0, 27, 10, 0, 1, negative 10, negative 3. We stop here. Why do we stop here? For 2 reasons. Number 1, I don't have a third equation, do I? We see that the solution is a line. So I need one of my variables to be a parameter, which is going to be z. Z is your parameter t. So this is what your solution is going to look like. You're letting z equal t. So it's going to look like this. X equals, excuse me, 10 minus 27t. Y equals negative 3 plus 10t. Do you see that? And then z equals t. So if you're using a matrix, you're only going to get the 1, 0, 0, 1, your z column, you leave, and it becomes your parameter t. Okay? Are there any questions? Okay. Given 2 intersecting planes, the cross product of the 2 normals gives the direction vector of the line of intersection. So let's talk about that. So cross product of 2 normals. What does the cross product of 2 vectors give you?
The line
fine.
perpendicular to both.
Yeah, good. It gives us a vector that is perpendicular to the other ones. Excellent. So here what we're doing is we're taking the normal of the 2 planes and we are going to cross them. And what it does is it gives us the direction vector of that line of intersection. Okay, the line of intersection. Okay, so refer back to example 3. This is just a reminder of how to do the cross product, right? You have two vectors. If the two vectors are 1, 2, 7, 1, 1, 3, -3, we write it twice. Ignore the first and last column, and we always multiply to the right first, right? And this is how you find your direction vector for the line of the intersection, okay? Direction vector for the line of intersection. Okay, so for example, use the Gauss-Jordan method to determine the intersection of planes x plus 2y minus 4z equals -7 and 2x minus 2y minus 5z equals 10. So I've got two planes. What do I do first?
Check normals.
Yep, check normals. I want to know, are they parallel or coincident, or are they going to intersect in a line? So I check the normals. Looking at the normals, 1, 2, -4, 2, -2, -5, I notice that one is not a scalar multiple of the other, and so therefore we know that these two planes are going to intersect at a line. Okay, normal 1 is not a scalar multiple of normal 2, or vice versa. All right, so it said in the example to use Gauss-Jordan method, so that's what I'm going to do. So I have 1, 2, -4, -7, 2, -2, -5, 10. What do I do? What's the first thing I need to do?
Make the 2 a 0.
Nope, it's before that. Before we make that 2 a 0, what do we do first? Oh, excuse me. Sorry, I apologize. You're talking about this too, correct? Yes, we want to make this 2 a 0. Sorry, Brian, when you first said it, I thought you were talking about this too. I apologize. So yes, we want to make that 2 a 0. And so I'm going to take equation 2 and I'm going to subtract 2 times equation 1, right? To get that 0 there. And so I'm left with 0, -6, 3, and 24, right? 10 plus 14 there. Okay, good. Now, what's the next thing we want to do?
Make the other two as
Yeah.
I mean, sorry. Okay, yeah, sure.
Yeah, no, it's okay. What were you going to say? Go ahead. Go ahead.
I thought they would make the like the -6 a 1.
We should. Absolutely. Make the -6 a 1. And I was going to do it in one step. That's why in 2 steps. But yes, we're going to make that -6 a 1. And we're going to make that top 2 a 0. Very good. Okay, so how would I make that? What should I do with that row? Take a look at that row. 0, -6, 3, 24.
Divide by -6.
Yeah, you can just divide it by -6 right off the bat to get it to be a 1. Okay, I have it in 2 stages here, I believe, but we can do it in 1, right? To get it to 0, 1, -0.5, -4. From here, oh, okay. So okay, so I'll show you what I did here, but either way is fine. So I made this into a -2 so that now I could just add the 2 equations to get me the 0 where I need it. But either way, it's fine. If I went straight to the 1 by dividing by -6, then I would just have to take that top equation and multiply it by 3, right? In order to eliminate. That's the only difference. Okay, so as I said to you yesterday, guys, not one way to do this, many ways to do this. Definitely quicker ways, but there are many different combinations, right? Okay, good. So now 1, 0, 0, 1, and then I have my Z column that I leave alone because that's going to be my parameter T. Okay, so here I'm going to have X equals 3Z plus 1. Sorry, guys, give me a sec. So X equals 3Z plus 1, but Z is equal to T. And then from here, I have Y equals a half T, or a half, you can see that, guys, a half Z minus 4. And Z equals T. So here is my solution. T is an element of real numbers. Okay, so What else can we do here? Well, I noticed that I have a fraction. So an even better solution, and you don't, again, you don't have to do this. This is still a valid solution, but a better solution is to make z equal to 2t. So that now you eliminate the fraction. Okay? That's more simplified. Are there any questions? Okay, so a little recap. We want to know how two planes intersect. So we check the normals. If the normals are the same, okay, or they reduce to be the same, then you check the d value. And if the d values also reduce or have the same scalar multiple as the normals do, then you know that the two planes are coincident. But if the d values don't match, then you know that the two planes have to be parallel. When you look at the normals are not scalar multiples at all, then you know that the two planes have to intersect at a line. And when you're intersecting in a line, if you think of a vector equation of a line, we know that you only have your one parameter, which we either use s or t, right? And so when you're solving, you're going to need that parameter t.
Miss, I have a question.
Yeah,
So how do you know that z equals t?
you're letting z equal t.
So would you
Just
just do
like
that for like all these?
I'm sorry?
So for like all these like types of questions, would you just let z equal t?
Yeah, because the reason is you have an infinite number of solutions, right? So that means t can vary. You're going to get different x's and y's depending on what t is,
Oh, okay, I see.
right? So you can basically make t whatever you want. And that's why here we know that when you have two planes, when you're talking about whether they're parallel or not, when there's no solution here, we now need two parameters, because now it's not a line. Our solution is not a line. Our solution is a plane, right?
Mm-hmm.
Where we had the two coincident planes, right? Where there was a solution. So we let z equal t, and oh, sorry, not this one. It was here. No, this is parallel. Where'd it go? I had it. Here it is. Okay, so we see that the two planes are coincident. So because they're one on top of the other, we need the solution of the plane. And because it's a solution of a plane, we need their two parameters there. So we use s and t.
Okay.
Okay,
Thank you.
no problem. Okay, so this is your homework, guys, for this section. It's page 516, 1A, 2A, 3A, 5 to 11. So 7E, the textbook is now, for this solution, letting y equal t instead of z. It appears wrong, but it isn't. They just chose y to be their parameter instead of z. Okay, and as I said, I normally tell the students on the test, always please let the parameter, use z for your parameter. Always let z equal t. Just for consistency. Okay, no questions, guys? Okay, so let's take a little break and we'll reconvene in 10 minutes. So it's 12:57. So let's say 1:10. Let's say 1:10, we'll start with the second lesson, okay?